First of all, the Tarski paradox and circle squaring. Tarski paradox motivated von Neumann to introduce amenable groups, and unlike in case of the free groups, as you saw, thanks to math, for amenable groups, no paradoxical decompositions are possible. And the most famous problem posed by Tarski was if the unit square and the circle of unit area can be equidecomposed. That was proved much later by Miklós Lackovics in 1990. And in the last 5 years, a number of nice results appeared, which made this equidecomposition also measurably possible, and later with Borel pieces and even Jordan measurable pieces. And so we reformulated this equidecomposition problem, so equidecomposition with a finite number of pieces via isometries in a more general context of graphings. So we rephrase them as perfect matchings in graphings. And in particular, since these come from amenable groups, the graphings we deal with are hyperfinite. And the advantage of having hyperfinite graphings is that every perfect hyperfinite graphing with a perfect matching already admits a measurable fractional perfect matching. So unlike in case of general problems, we already have a measurable fractional perfect matching to start with. And we saw that at least in the odd regular case, this was already enough, just rounding or fractional perfect matching along cycles using circuits, using that the graph is bipartite, allowed us to get an integral solution, so an eventual perfect meshing. One player, the main antagonist mentioned, but this didn't play any role, is the counterexample also due to Lackovics. This is the graphing of irrational rotation. So we take an irrational number and the vertex set is the closed circle as to the one, and two vertices are adjacent if their angle is theta or minus theta. So this has no measurable perfect matching, as you have seen, you will see, I really hope you will see, I really hope very soon after lunch. And I also suggest to add the Bernoulli shift of the group of integers z to this, that also with the standard set of generators, it does not admit a measurable perfect matching. So we will see that somehow the two-ended graphings will cause the problem for us. Not yet.
Maybe with the keyboard.
Okay.
Because
okay, let's play. Keyboard is okay. I want. Oh, I'm okay with the keyboard, but and I can't find the PDF. I think it's not a big issue. Okay. Oh, boys. Don't need too much technology. Okay. Will be enough, but I should write slides because I'm capable to forget about important conditions, and that would be a disaster. So next I speak about toast structures called toast. So we are heading towards somehow finding the reason why these irrational rotations are bad, and so we will identify some structures that help us. One that many of you have already probably faced are called toast. It's quite an unfortunate choice of name, to say the least, but the picture, well, there are of course more realistic pictures, less informative ones, but the point of the toast is that it's a kind of refinement of hyperfiniteness. So in case of hyper, we know that there is a sequence of finite relations, so equivalence classes are finite, and it's a countable increasing sequence, and in the end we get the full relation. So every orbit or in this countable equivalence relation will be one class in the union of these. And so how we imagine it, that we have the small red classes as first relation, then come the blue ones, the green, and so on. So in this case, it's a bit stronger, though essentially equivalent to hyperfiniteness, that not only it's an increasing sequence, but we have a collection of finite connected subsets. I call them Borel because I don't care about null sets. So and it's PMP, the graphing. And so in case we have this sequence of relations, we can we think of it that taking just every class from this sequence of relations. But we have some extra conditions that in case two classes are disjoint, they should be far away, so there is no edge going from one class to the other if they are disjoint. And in case one class contains the other, then it should also contain its neighborhood. This is described with these three small middle conditions. And of course, the union is still all of the graphing everywhere or almost everywhere.
Is the condition redundant, or am I just not parsing things correctly?
Martin, is it? It's your slide.
Third point
It's something by K. Oh, that's can.
Yeah, it's ridiculous.
Yes. Thank you. Yeah, it's a good start. Please keep everything.
Slides are bad.
Oh, there are only a couple of them. But for this wonderful picture, it was worth it. So in any case, this is the picture what we have in case of toast. And also, for example, you should imagine it that would have no edge, for example, between this blue X here. Well, more generally, they like to speak about K-toast. Not only that we don't have edges, but they are far from each other. The distance is at least K. So this is something what clearly shows where we are heading to. It's a useful structure. So if we want to solve a problem, give an algorithm, then we start with the red finite parts. We solve our problem, I don't know, we round our fractional perfect matching. Then we go to the blue parts, the green parts, and so on. We go to infinity. So even though Damian did not allow to choose one point to start from, but here we start from many but finite parts and we just build it up. But what will be more useful for us is called connected toast, where we are happy with having with the one toast, the distance should be one. But if we take a piece of this toast, one set in the tiling, then if we remove the smaller ones from this, then the difference will be connected. I think this is still easy to imagine that it will be a very useful condition when working. And this, of course, does not hold for every hyperfinite structure anymore. And you may have an educated guess which ones that will be, where we can find connected toasts. So if it's clear, then I go on.
Just toast also doesn't exist for all hyperfinite graphs.
In the measurable case, it does.
Yeah, okay.
Oh, sorry, I only have heard of the measurable case. Or I can think about it for 5 minutes, what happens if it's not measurable, but maybe this is not the, but there is help on the way in any case.
Yeah, sorry, just to get some intuition, if we look at the previous picture we had, would this be connected?
So you have this simple line, the we're going to say free action of the Z. Then you take long intervals. These are lengths 100 with gaps between them. Then you take 100 consecutive intervals to be a bigger piece and so on. You exhaust the whole thing, but the difference will be just that from a long interval, you remove many shorter intervals. So it won't be connected, and yeah, so certain things will be less possible.
But this one on the picture is connected.
Oh, well,
I'm not sure that is part of the group.
The red books are one thing.
The green is thin, so
I think it's,
yes.
this is debatable, let's put it that way. Depends on your eyes and glasses.
Yeah, it's questionable.
Okay, so yeah, I guess we said that. So I'm somewhat embarrassed in the next couple of slides. I might be the one in this room essentially who knows the less about ends of graphs, but in any case, a few words should be said. Just it will be important to us. So, well, in graph, if you wish, is just a simple shell complex, one-dimensional one. So you have a good picture what ends are here. But so then the race will be just semi-infinite paths. So injective random walks that start at some point and go somewhere to the infinity. Race will be equivalent if there is a third one that goes from one to the other, there, back. So you know the picture here is one, there is another one, and if we are in the plane, then it's easy to see that these are equivalent, just the third one switching from one to the other and back. So this is what defines an equivalence relation for us on the race. And so just a couple of basic examples, the square grid and the line. So in case of the line, of course, we have two ends, and we don't even have too many really different semi-infinite paths. But also, even if the line was thicker, so it was, I don't know, an infinite by 10 line, then also going there and back could be only performed finitely many times. So it would still have its two visible ends. Unlike in, say, case of z squared, the square grid, where we have this picture and we have only one end as well known. Since you may imagine in hyperfinite graphings, we won't have too many ends in the end of the day. So we can also characterize them by finite cut sets, that we have at least k ends if there is a finite set, say connected one, that after the removal of this, we have at least k infinite components, and who knows how many finite ones. This will say that it has only finitely many ends. Of course, I have only locally finite graphs in my mind now, so every infinite component will contain an array. Oh, yeah, I think that's not a point to stop. And we saw that theorem, what might be its first form dedicated to Hopf, says that every locally finite graphing has almost everywhere infinite or 0, 1, or 2 ends. Here I don't specify what kind of cardinalities may come up here, especially because, as you see on the bottom of the slide, our case, this cardinality will be at most 2. So we have only 3 options in the hyperfinite case. Maybe for those who haven't seen this, I just say a few words why intermediate options are not possible for graphing, say, having 3 ends on a positive subset of the vertices. So assume that we have a component which has 3 ends, so we have a cut set, and we have 3 infinite.
Right now, you're sketching the Adams statement, or
Oh, no, that's one that you cannot have something between 2 and infinity. I don't, just to get some picture, I guess, and some finite parts here and there too. So we have these 3 infinite parts. And so first of all, if we have this cut sets which cut it into three infinite parts, they cannot be disjoint. What if they were disjoint? Say, proved by example, if there was one here that has again infinitely many components, then one component should be what's now on this right side, and we would have two more infinite components, the picture, and possibly finite ones. So suddenly we could have realized that we started with a component promised to be free-ended, and suddenly we realized that we have four infinite components after these cuts, all would contain a ray, and this would be not equivalent because this would be cut away by finite sets. And knowing that they cannot be disjoint, we just take a dose of minimum size in every component, and their union, because of locally finiteness, would be still a finite set. So this would mean that in these parts of the graphing where the number of ends is finite, but strictly bigger than 2, we would find a finite connected subgraph, and so we could also find in a finite graph just one single vertex. So we would pass against Damien's commandment that we could find a kind of finite selector like Vitali once upon a time, and this would prove that these components have a union which is a null set. So that's the general idea or the typical thing behind these theorems. So we have a limited number of possibilities. And of course, if a locally finite graph has 0 ends, then it should be finite. And so all we care is the 1 or 2-ended case. Oh, the other computer. And so 1-ended case will be our favorite, and here is the list of equivalent conditions for a locally finite, hyperfinite graphing being 1-ended. First of all, that it's 1-ended in almost every component. And then a useful one which shows that somehow the rest is really a degenerate, the 2-ended case is really degenerate, is that in case the balls have superlinear growth almost everywhere, then it guarantees that it's 1-ended, meaning by superlinear growth that the volume as a function of the radius r should be greater than c times r for every c, sometimes for an r. The third one is a connected toast, but again, not very hard to get, but and the most interesting one is by Robin, Damien, Clinton Conley, and Andrew Marks, that and also Adam Timar did it for the factor of IID case, though Robin and the others did not concentrate so much on hyperfinite graphings as you could, if you remember Damien's talk from yesterday, that these admit a 1-ended subtreeing. Now let's a bit careful compared to Damien's talk. Here a 1-ended subtreeing means that almost every component will be just 1 tree in the hyperfinite case, and not a collection of trees. So it's for us it will make a tremendous difference. So these are quite nice the equivalent conditions, and I wouldn't call them as an exercise, but if somebody has to work with 1-ended graphings or amenable groups which are not virtually Z, the later ones are the 2-ended ones. And
Ignore that. think this is another one of the questions.
Yes, sorry, that was a K-toast once upon a time, but please ignore it.
Yes.
Yes.
So is it equivalent to have a K-toast for and
Yes, it's if you can switch from, if you may wish, you when instead of the original graphing, you can look at the one where those vertices are connected, whose distance is at most k. And since somehow being hyperfinite is not such a combinatorial property for graphings, but it's really a property of the equivalence relation, it won't really matter what's the underlying graph. So these constants can be bypassed.
I think that's not true. I think for k bigger than 1, you can't have a connected K-toast. You can certainly have a connected.
I suggest this to be an exercise.
No, so you can have a K-toast measurably, but I don't think you can have a connected K-toast measurably. Yeah, there's the.
Okay.
Anyway.
Let's postpone it at least till after the talk.
So your last statement, you said it was not the same as in Damien. So you mean?
Oh well, it says it's in their paper and it's not the same. I want to emphasize that in the case of Damian, he was usually interested in that every component is a union of possibly many one-ended trees, and here there will be only one. So that's the important point, that it's a spanning subtree. So not a subforest. Thank you. So it makes the big difference now. So because, well, having just a tree in one component, it's at least easy to imagine the process how to build a toast. It might not be that easy, but we have this tree, and so it goes up to infinity, and below every vertex there are only finitely many others. And the natural choice for a piece of toast that we take one vertex and all of its finitely many ancestors, and this is a good start. And if we work along these lines, we can refine this using Borel-Cantor lemma and similar things to get this toast almost everywhere. But somehow my favorite from this list is the one-ended substring. So let's prove it at least give the proof by a picture, kind of. So assuming the others, especially the, say, connected toast, or in fact only the toast. So we have these smaller pieces of toast. We write a tree in all of these. Then we start to connect the trees. Of course, what's not so great in the picture, there might be vertices which are not in these four blobs with the red trees, but still in the big circle, and those are also connected. So we just build up this tree piece by piece from to larger and larger pieces of toast, and it will be a hyperfinite tree. So there aren't many options for it. It can be one or two-ended, and one needs to think a tiny bit about it, but if one chooses carefully these parts, then one can make it one-ended using the condition on superlinearity, so that the volume of the balls grows superlinearly. So if once we have some fixed pieces of toast, small ones, and then we take the next one much larger, we choose a few vertices in it, and take the Voronoi cells, then locally the picture what we will, and we direct every vertex towards the center of this Voronoi cell, then locally we will see the same picture as in the original graph. So it grows superlinearly, and we can connect these pieces to get a larger tree. And so the tree what we build will be in such intermediate steps of large growth. So for almost everywhere we will get some large growth. It's
this is different than their proof and the guidance proof, right?
Yeah, so it's different than what's in our paper, but the combination.
I took it from March in the picture.
No, it's different, but it's nice. It's slightly different proof.
Yeah.
It's just because, well,
It's from the book, in our paper, we didn't.
yeah, well,
So.
yes, so so these things were have appeared in quite a number of papers. I could have added a lot of names like Tom Hutchcroft and Benjamini and earlier ones, but somehow nobody took it very seriously to write it up properly, to be honest. I hope the future will find that we did, so we added this to the appendix. But truth is that working with two-ended graphings is so boring that one tries to minimize the time spent with those. Okay, so
Gabor, there is a question.
Just to kind of clarify, what do you mean by noise cell?
So you choose a number of vertices in this large graph. Your metric is just the graph distance, and then you choose from this large maximal kind of dense set. So a kind of net for every vertex. To every vertex, you choose a closest one among this set. And then you build in every Voronoi cell this tree. On the boundary, you don't care which choice you make. And once you have these trees will have, well, locally superlinear growth themselves. It's a local condition. So for most of them, for a fixed constant C, the R we have found will work. And then we just connect them to make it a tree again, and we continue in this fashion. So almost every vertex or every vertex will almost surely be hit infinitely many times in this process, and so it will often have large balls centered at it.
So there's an easy if but it's not the
So I think it's just to give a picture and the idea that there is some refinement, but I prefer to use it now. I really suggest for those interested in to elaborate on this. I think I don't need to give the advice to everybody. Anyways, so what I wish to concentrate on is our main theorems with Matt and Martin. Oh. It's no. I hardly gave any talks when I taught, but I prefer these exercise classes, and I was so happy that students were active. So please don't stop. It's a much better feeling. Oh, so some theorems. So finally, we can state our theorems and identify what's bad with the irrational rotations. And so still we have hyperfinite bipartite graphings, but let's think of the case when it's nowhere two-ended, so components are either one-ended or finite, what's less interesting, and it has a measurable fractional perfect matching, and in this case it has a measurable perfect matching. And remember that in case we have a perfect matching, we always have a measurable fractional perfect one. So on the next slide, I will show you an example where we need this non-integral condition. So somehow the fact itself that the graphing is one-ended is not enough, but we need the support of this, or where this measurable fractional perfect matching has values strictly between 0 and 1. This set should be one-ended. So if
again, but I don't understand your remark.
you will understand it on the next slide, my statement is. So this is a bit complicated theorem, and the question is, why is it not the theorem that every one-ended hyperfinite graphing which satisfies the whole condition and is bipartite admits a measurable perfect matching? And you will see that it's not true.
You need the assumption of the existence of the fractional perfect.
Yeah, my statement is that this is an optimal theorem. We worked on it quite a lot, and we tried to remove every damn word from it, and that's how we managed. And now I try to argue later that the damn words left here are unfortunately necessary, at least in this language. So it's, well, as von Neumann said, we don't understand mathematics, but we get used to it. So but at least in the regular case, there are some cute consequences that, of course, in the regular case, we have a fractional perfect matching. And so in the one-ended regular case, then we have the matching if the graphing is bipartite. And we saw last time that somehow this exceptional odd degree case only requires being one-ended. Somehow that guy cannot appear there.
Sorry, so regular meaning.
Every degree is the same.
Got it, okay.
So somehow accidentally last time I mentioned that in the odd degree case, hyperfiniteness is enough. We don't need being one-ended. It's an accident. So in fact, no, in fact, let's see the first example. So we want to consider a graphing that every component looks like this. So we take this square grid, and on the horizontal edges will be replaced by these two edges and the force cycle in between. So how does a perfect matching look like in this graph? First of all, we have the upper and lower point in every force cycle, so this should be connected to the other 2 points of the force cycle. So in every force cycle, we have this or that matching, and the same for fractional matchings. So the force cycles themselves are kind of independent. This means that the lines from a force cycle to a vertical line, the edge cannot be used for any perfect matching. So perfect matching wise, these really horizontal edges are absent. So we have in practice vertical lines and force cycles independently. And then it's not hard to do the graphing using these irrational rotations, for example, and modifying them where we really will see this. And if we remove the force cycles, then the lines won't admit a perfect matching. So there are multiple ways to realize it. It's not depending on one's taste. Bernoulli shifts of some kind of quasi-transitive unimodular graph or just these irrational rotations. So from a reaction of z square, one can build.
But that won't have a fractional perfect matching.
I mean, the irrational rotations have a fractional perfect matching 1/2. Yes.
Put one half on the vertical lines and one on yes inside of the yes.
So just
so it's not positive actually. Oh, okay, so it's not positive everywhere.
Yeah, it cannot be positive on those on the horizontal edges, so they are absent matching wise. Of course, one can also state this is in a different form, but in the hyperfinite case, that's not needed almost everywhere, that we have the whole condition, and one can also define the measurable whole condition that the neighborhood of the set should have measured at least the size of the set, and if this is sharp at some point, say from the set S to its neighborhood, and its NS has the same measure, then we basically cannot use the edges from this neighborhood going elsewhere for other purposes. And in the hyperfinite case, we can realize this locally, but in case of say other group actions or other graphings, this is more sophisticated, but here we see this combinatorially.
Yeah.
Sorry, guys, can you just for a second go back to your previous slide?
Yeah, anyway, it was my wish, thanks.
Also, the term non-integral, it means that there are no zero.
That's not 0 or 1.
Okay, so
in fact, well, one can speak about the support only because it's strictly it's in the 0-1 interval, but our theorem also holds in case we have a mapping f from the set of vertices to the non-negative integers, and we want the sum at every vertex to be exactly this integer. So somehow the philosophy, as in, I don't know, this operation research or similar fields is that we have some fractional solution and we make it integral. So maybe positive would look here better, but somehow but non-integral is the, say, consistent way to say it. And in fact, in some algorithmic sense, though not every co-author may agree with me, this gives a characterization of hyperfinite graphings which have matchings, because one can find, given a hyperfinite graphing, maximal one and the right fractional perfect matching, such that this is essentially maximal, where it's non-integral, and then we look at the rest, and if it has two-ended parts, then we have to solve the two-ended parts as they are. So this reduces to the two-ended case the problem of finding a perfect matching in a measurable way. Okay, so
you don't need to assume some kind of a core condition.
it's regular, so that saves the effort for us. While otherwise it's by the fractional matching. Yeah.
Externally, so do you have examples of two-ended graphings that meet non-integral fractional flow, fractional matching, but then doesn't have a measurable perfect matching?
Two-ended graphs that does
Do admit non-integral measurable fractional perfect matching.
Yes, regular. So there are regular ones, which I think the last slide last time had something like so. The Lackovich has a two regular example, and then there are by I think Conley and Carris. Well, okay. So this can be done. We may return to these borderlines a bit later, but yeah. So now we concentrate first on applications. The most direct thing is just looking at the Lyons-Nazarov theorem. So this said, it said it quite quickly last time, in half a minute given by Marcin, that the Bernoulli shift of a non-amenable group, if it gives a bipartite graphing, then it admits a factor of IID perfect matching. No, sorry, the Cayley graph admits a factor of IID perfect matching, or surely or equivalently the Bernoulli shift has a measurable one. And this left the question open, what's the case of amenable groups? And it turns out, since the amenable groups are handled by our theorem, the regular theorem, what's left here is the two-ended case, what's virtually Z. And it turns out that the semi-direct product of Z and the finite group of odd size is the case when there is no matching. So that's why I asked to look at the Bernoulli shift of Z besides the irrational rotations. I think it's enlightening. And then in case of measurable circle squaring, we gave a couple of new proofs, though like the other proofs, these simply rely on the fact on Lackovich's result as a black box. So what I want to show now, it relies on the fact that random translations can be used to give equidecomposition of the square and the circle. And what we show is that in case that this will be enough for the measurable circle squaring. And we have a funny probabilistic application thanks to Adam Timar, who just on Poisson processes. So he taking two random subsets in R to the n, a Poisson process, he looked for a matching between these subsets, say, of course, with the same intensity, say 1. He looked for a matching and he looked at the tail of this matching and he managed to solve this problem kind of optimally, at least according to the present state of science. So this was a problem started by these probabilists. And also I will speak about balanced orientations, what quite a few people worked on in the audience. So any questions to Lyons-Nazarov? If no, then we will see the rest. So by a balanced orientation in a graph where we assume that the degree of every vertex is even, we mean an orientation of the edges that the in degree and the out degree equals for every vertex. And so Riley and Ferenc Bench with Aranka and Laci proved a number of results on this. I just mentioned that a case of expander graphings or non-amenable quasi-transitive universe, there were graphs in the later case, and also in the two-ended hyperfinite or amenable case, they gave a number of counterexamples, which and posed the question what happens with the one-ended case, or to be more precise, when it's meaning the hyperfinite one-ended case when it's not quasi-isometric to Z. And the answer is that here one can the two problems of finding a balanced orientation, or the problem of finding a balanced orientation in a graph, can be reduced to finding a perfect matching in another graph. So on the picture we have the square grid, the vertices are labeled all with 2, and then we take a barycentric subdivision of this. The new vertices are labeled by 1, and if we take matching of this new graph, this will be in one-to-one correspondence with the a perfect matching which covers, well, the vertices of the original grid twice and the middle vertices once. This will be in one-to-one correspondence with the balanced orientations of the grid, whatever graphing or structure we worked with. We just take this path of length 2 between two grid vertices and we orient them towards the matching edge. So it gives a quite direct connection.
That should be MFPM?
Probably I'm not. Yeah, it should be measurable somewhere.
There's no F that is.
No, it's not, yeah.
Because over here he says above. Okay, it shouldn't.
Right, the grid axis even. So this is always a.
Okay, so you're defining. Okay.
I hope
Then the FFPM.
that's a fractional perfect matching. And so at every vertex here, the degree was 4 everywhere, but in general, we want to find a matching, general matching, that every vertex is covered by the half of the degree, yes?
The letter F is missing. When you have degree over 2, M, that
PM, you define above what a function dash FPM is, and then you use some new terminology that isn't defined there.
M should be
a function.
Measurable perfect matching. So F is yeah. So that F should be an that F should go the capital F. Yes.
The capital
F is also correct. There's just another.
No. That's fine.
The point I think is that if you want a balanced orientation, then the solution downstairs cannot be fractional. Yeah. So the the bottom NPM should read as measurable perfect matching.
Okay, I guess I just didn't know. I was not aware what a measurable perfect matching is.
Sorry.
You already explained it.
Reminders can. So just it's a mapping from the set of edges to the 0-1 interval that the sum at every vertex is 1. So in particular, if it's a matching, it's 0-1 valued, and and if you have an odd cycle, then it can be half everywhere. So that's something easy to handle. And the point is that I started for hyperfinite graphings. If the whole condition holds, then we always have a fractional perfect match.